In section 2.4, we look at the average rate of change of a function. The average rate of change of a function y equals f of x between x equals a and x equals b is defined to be f of b minus f of a divided by b minus a. And this average rate of change is nothing more than the slope of the secant line between x equals a and x equals b on the graph of the function. So if you go to the function here, we have x equals a, and here's the point on the function at x equals a. And at x equals b, here is the point on the function there. And this average rate of change is nothing more than the slope of this line. And this line is called the secant line. Secant line is a line that intersects the function in two distinct points. Let's take a look at a quick example. Let's suppose f of x is equal to the function x minus 2 quantity squared. I want to find the average rate of change from x equals 1 to x equals 2, and then from x equals 3 to x equals 4. And we can do this without using any kind of a graphing aid. The definition for the slope of a secant line, or the average rate of change, is f of b minus f of a divided by b minus a. And for this problem, a is 1 and b is 2. So f of b minus f of a is f of 2 minus f of 1 divided by, and then b minus a would be 2 minus 1. And then we have to go ahead and compute those function values. So f of 2, we're going to plug 2 into the function. That gives us 2 minus 2 squared, which is 0. And f of 1 is equal to 1 minus 2 squared, and this is equal to 1. So f of 2 minus f of 1 is 0 minus 1, and then divided by 2 minus 1, and this is negative 1 divided by 1, which is negative 1. Now let's go ahead and bring in a sketch of what this looks like on a graph. So here we have the function y equals x minus 2 quantity squared, and then here is that secant line. So I want you to notice that it passes through the function at this point here, so this is where x equals negative 1, and also at this point here, that's where x equals 2. And the slope of that line is negative 1. And that is what the average rate of change is equal to. Now let's take a look at the second part. Let's find the average rate of change from x equals 3 to x equals 4. So to do this, we basically use the same exact steps. The secant line has a slope of f of b minus f of a divided by b minus a. In this case, a is 3 and b is 4. And so this is going to be f of 4 minus f of 3 divided by 4 minus 3. And now we just need to compute those function values. F of 4 is going to be 4 minus 2 quantity squared, which is 4. And f of 3 is 3 minus 2 quantity squared, which is 1. And so this average rate of change is going to be 4 minus 1 divided by 4 minus 3, which is 3 divided by 1, which is equal to 3. And we can go ahead and bring in the graph to see the secant line here. So once again, we have our function, y equals x minus 2 quantity squared. We have x equals 3, which is right here, x equals 4, and here are the 2 points on the function corresponding to those values of x. And this value of 3 is the slope of this secant line. So graphically speaking, the average rate of change of a function is the same as the slope of the secant line. Now let's take a look at a slightly different type of example. In this problem, it says that if an object is dropped from a high cliff or a tall building, then the distance it has fallen after t seconds is given by the function d of t equals 16t squared. Find its average speed, which is the same as the average rate of change, over the following intervals. So for part A, we're being asked to find the average speed or the average rate of change between 1 second and 5 seconds. And so this is when t equals 1, changing to t equals 5. So from 1 to 5. Now the function here is d of t. So the average rate of change is going to be d of 5 minus d of 1 divided by 5 minus 1. So it's exactly the same thing that we did in the last problem, but this time I'm not going to draw a graph or anything like that. We're just going to compute this algebraically. So first of all, d of 5 is going to be 16 times 5 squared. So this is 16 times 25, and 16 times 25 is 400. And d of 1 is 16 times 1 squared, which is 16. And so d of 5 minus d of 1 is 400 minus 16 divided by 5 minus 1. And if you do the math on this, this is 384 divided by 4. And this is equal to 96. Now there are some units associated here. D is the distance, and the distance is given in feet. And t is the time, and t is given in seconds. And so when you do the subtraction in the numerator here, this is measured in feet. And in the denominator, this is measured in seconds. And so the units on our answer here are going to be feet per second. And so this is the average rate of change of the distance that this object has traveled, and the average rate of change of the distance is the same thing as the average speed. In part B, we're doing the same thing, but this time it's a little bit more theoretical. Now we're changing from t equals some unknown value a to some other unknown value, which is a plus h. And we want to find the average speed or the average rate of change. So it works the same way. We're going to do d of a plus h minus d of a divided by a plus h minus a. So d of a plus h is going to be 16 times a plus h to the second power. So again, I'm just plugging that into our function here, right? Because the function is 16 times t squared. So we're just replacing t with a plus h. And then we have minus d of a, which is 16 times a squared, and all divided by, in the bottom we just have h because these cancel out. So now we just need to do the math here. We need to multiply this out. So what we have here is 16 times a squared plus 2ah plus h squared minus 16a squared, all divided by h. Next step, we distribute 16. So we get 16a squared plus 32ah plus 16h squared minus 16a squared, and again, all divided by h. And it looks, bad at first, but it always gets a little bit better as you progress in the problem. So we have 16a squared minus 16a squared. Those cancel out. And then, as you've seen now in a few other examples, if you look at the terms that are left here, you can factor out an h there. And when you pull out that h, that will allow you to cancel that h with the h in the denominator. And so we end up getting 32a plus 16h. And of course, this is also feet per second. So this is just a quick lesson on average rate of change. It's not terribly complicated, but it is an important concept, especially in calculus. One other concept that I want to point out to you is that when you have a function that is increasing, so here we have an example of a function that is increasing. If you go from point A to point B on the curve here, and you look at the slope of that secant line, you'll notice that the secant line will have to be going upward, right? So in other words, the slope of the secant line has to be positive. And this is always going to be true for a function that is increasing. So anytime a function is increasing, its average rate of change must be positive. Now, likewise, if a function is decreasing, now when you look at the movement from f of a to f of b, the slope of this secant line is going to be negative, and that's because the function is going down. So anytime you have a decreasing function, the average rate of change is going to be negative. Let's talk about one other concept. Consider a linear function. Now, a linear function is just a line, and so we can represent a linear function by saying f of x is equal to mx plus b, where m is the slope of the line and b is the y-intercept. Let's compute the average rate of change of this line for two randomly chosen values of x. So let's suppose we're changing from x equals 2 to x equals 6. So the average rate of change we know is going to be f of 6 minus f of 2 divided by 6 minus 2. Now, f of 6, we're just going to plug 6 in for x here. So when you plug in 6, you get m times 6, which is 6m, plus b, minus, and then f of 2 is going to be m times 2, which is 2m, plus b. And we're going to divide that by 6 minus 2, which of course is 4. And then if you distribute the negative sign here, you're going to get 6m plus b minus 2m minus b, all divided by 4. And if you do the math on this, b take away b cancels, and 6m take away 2m is 4m divided by 4, which is equal to m. So notice that the average rate of change of the linear function is just the slope of the line. Now, is that a coincidence or does that always happen? Well, it turns out that it always happens, right? Because if you graph a line, y equals mx plus b, it has a graph that looks something like this. And if you pick any 2 points on that graph and you draw the secant line, notice that the secant line is the same as the line itself. So of course the slope of the secant line is going to equal the slope of the line. So basically the average rate of change of a linear function is always a constant, and it's always equal to the slope of the line that you had to begin with. All right, so that's it for this one.